This video will cover lithium aluminum hydride reduction of carbonyls. Lithium aluminum hydride consists of a positively charged lithium ion and a negatively charged aluminum hydride ion. Notice the similarities between lithium aluminum hydride and sodium borohydride. However, since aluminum is less electronegative than boron, hydrogen has a larger partial negative charge and therefore is more reactive than it is in sodium borohydride. Let's look at the general reaction. Typically, a carbonyl is treated with lithium aluminum hydride, followed by an acidic workup to protonate the alkoxide ion that is formed. Notice that these two steps must be done sequentially, otherwise the lithium aluminum hydride would be quenched by the acidic workup prior to reducing the carbonyl. Now let's look at the mechanism. In the first step, the aluminum hydride attacks the carbonyl carbon, producing the tetrahedral intermediate. In the second step, the alkoxide ion is protonated by the acidic water to produce the alcohol. Now let's look at some specific examples. Just like sodium borohydride, lithium aluminum hydride can be used to reduce an aldehyde. For example, if we treat this aldehyde with lithium aluminum hydride followed by an acidic workup, we get a primary alcohol product, just like with sodium borohydride. We can also use lithium aluminum hydride to reduce a ketone. For example, if we treat this ketone with lithium aluminum hydride followed by an acidic workup, we get a secondary alcohol, just like we saw with sodium borohydride. However, because lithium aluminum hydride is more reactive than sodium borohydride, we can also use it to reduce less electrophilic carbonyls, such as carboxylic acids, such as this one. Treatment of this carboxylic acid with lithium aluminum hydride followed by an acidic workup gives us a primary alcohol. We can also use lithium aluminum hydride to reduce an ester. For example, if we treat this ester with lithium aluminum hydride followed by an acidic workup, we also get the primary alcohol. The mechanism of this transformation is a little different than the previous one we looked at. However, it bears a striking resemblance to the addition of a Grignard to an ester or a carboxylic acid chloride. In the first step, the hydride ion attacks the carbonyl carbon, forming the tetrahedral intermediate. In the next step, the carbonyl reforms, kicking off the leaving group. A second equivalent of aluminum hydride reacts with this aldehyde, forming a second tetrahedral intermediate. This alkoxide ion is protonated following the acidic workup to produce the primary alcohol product.